Hello everyone. Today we are going to talk about the chemical properties of the polymers. And to understand that property, we need to learn about the solubility, degradation, and refractive index. The discussions on the solubility is prepared by MD Rashidul Islam. The discussion on degradation is prepared by Nasif Mahmood. And finally, I prepared the refractive index. And I am Nafisa Amin. So what is solution? Solubility is a property of solid, liquid, or gaseous compound called solute to dissolve in a solid, liquid, or gaseous compound called solvent. Solution is a homogeneous mixture of solute and solvent. The number of solute and solvent can be greater than 1 depending on the experiment. So what is solutions? A solution is a mixture formed when one or more solutes dissolve in a solvent. Here, an example of sugar solution is displayed, where you can see in the first glass the water, which is the solvent, and the sugar, which is the solute, can be seen clearly, but when it's mixed together there is a clear sugar solution on the right side. Classification: coarse particle containing solution, where separation is easy. The second one is the colloidal solution, and it is a mechanical separation. And the third one is the true solution, where separation is comparatively harder. So what are the expression of concentration? We need to know some quantities in order to understand the concentration of a solution. So the first one we need to know is the percent by weight. Next we need to know about the mole fraction, then molarity, next molality, next normality, and finally parts per millions. The factors affecting the solubilities are nature of solute, nature of solvent, which can be both polar and non-polar, temperature. If temperature is high, then solubility would be high in most of the cases. And finally, the pressure, and the relation between the pressure and the solubility is, if the pressure is high, the solubility would be higher, and this basically applies for gas. Here a curve of solubility has been shown, where you can see on the right side there is a chart where solubility versus temperature for a variety of salts have been displayed. In the x-axis we have temperature, which is in degrees Celsius, and in the y-axis we have solubility, which is gram per 100 gram water. And they have shown it for 5 different polymers. For some substances, solubility decreases with temperature, which you can see at the plot for cerium sulfate. For some substances, solubility increases with temperature, such as disodium hydrogen arsenate and barium nitrate, etc. And there are some substances where solubility slightly increases with temperature, for example sodium chloride, and for some substances solubility curve is discontinuous, such as sodium sulfate. Now we are going to talk about the Henry's law. Henry's law states that the solubility of a gas in a liquid is directly proportional to the pressure of that gas above the surface of the solution, and the law can be written as concentration is equal to the Henry's constant, which is denoted as K, multiplied by the pressure of the gas, which is denoted by P. An example of the Henry's law is shown on the right side, where you can see when the pressure above the solution is released, which is decreasing, the solubility of the gas decreases, and as the temperature increases, the solubility of the gas decreases. Limitation of Henry's law. The law is generally applied on the gas with ideal behavior in solution. Applicable for moderate temperature and pressure if the solubility of gas in the liquid is low and the gas should not react with the solvent. Solubility of solid in liquid depends on the chemical interaction between solid liquid compound, and the following are electrical force, hydrogen bonding, van der Waals force, and London disperse force. Now the questions are, what kind of solution can be reformed with water salt combination and water sand combination? Which compound has discontinuous solubility curve? Can we mention a compound with continuous solubility curve? What kind of chemical interaction happens in the solution of solid in liquid? And can we state the Henry's law? We hope that after looking this presentation, you will be able to answer these questions. Our next topic is degradation. So what is degradation? It is mainly the changes in chemical structure, and it is a physical property which leads to loss of properties, that is tensile strength, color, shape, and many more. And these loss of properties happen in polymers or polymer based products due to the influence of processing condition and other environmental factors such as heat, light, or exposure to chemicals are included within polymer degradation. Now we are going to talk about the mechanisms of degradation. The amount of time to have a certain degree of degradation depends entirely on the type of polymer, morphology, molecular size, and finally the conditions to which it is subjected. The process by which polymers can suffer degradation are thermal, mechanical, hydrolytic, chemical, and biological. Another degradation is known as photo-induced degradation, where exposure to ultraviolet or UV radiation may cause significant degradation of many materials. UV radiation causes photooxidative degradation, which results in breaking of the polymer chains, and it produces radicals and finally reduces the molecular weight. It causes a lot of deterioration of mechanical properties and leads to useless materials after an unpredictable time. An example of photo-induced degradation is shown on the right side, where the before and after exposure to UV light has been explained. Another type of degradation is thermal degradation. In polymers, thermal degradation refers to damaging chemical changes which take place at elevated temperatures without the simultaneous involvement of other compounds such as oxygen. At high temperatures, the components of the long chain backbone of the polymer can break, chain scission, and react with one another, cross-linking, to change the properties of the polymer. An example of the thermal degradation is shown on the right side, where you can see temperature is in degrees Celsius at the x-axis and the percentage of sample volatilized is shown on the y-axis. And there are more than one of polymers showing how they are affected gradually by the thermal degradation. Another type of degradation is chemical degradation, which involves a change of the polymer properties due to a chemical reaction with the polymer surroundings. There can be three ways to have a chemical degradation. One of them is solvolysis, where step growth polymers like polyesters, polyamides, and polycarbonates can be degraded by solvolysis, mainly hydrolysis to give lower molecular weight molecules. The hydrolysis takes place in the presence of water containing an acid or base as catalyst. Next type of chemical degradation is ozonolysis. Ozonolysis is an organic reaction where the unsaturated bonds of alkenes, alkynes or azo compounds are cleaved with ozone. And finally, oxidation plays a great role in chemical degradation. The polymers are susceptible to attack by atmospheric oxygen, especially at elevated temperatures encountered during processing to shape. Biodegradation. Biodegradable plastics can be biologically degraded by microorganisms to give lower molecular weight molecules. The term biodegradation indicates the predominance of biological activity in this phenomenon. In nature, biotic and abiotic factors act synergistically to decompose organic matter. A flowchart of the biodegradation is shown on the right side. So now comes the questions. Let's see if we can answer these questions. What do we think about degradation of polymers? When it is a desirable property and when it is not? Forensic polymer engineering is the study of failure in polymer products. Do you think principles of degradation can be applied here? If so, how? We hope that after listening to this presentation, you will be able to understand and answer these questions. The last topic of this presentation is the refractive index. So what is refractive index and why it is so important? One of the most important chemical properties of polymers is the refractive index, and it is denoted by N. It is also very crucial optical property for any kind of optical applications of transparent polymers. Every material has its own unique refractive index, and these characteristics of a material can be used for identification purposes or for predicting any other properties of a material. On the right side, an animation of refractive index is shown, where you can see how the waves are changing their course from going from one medium to another, and this happens because of the refractive index. So what is refractive index? When light is traveling through a medium, the light ray bends, and the measurement of the light bending is referred to as the refractive index of the medium. Another way to think about the refractive index is a measure of how fast light waves passes through a given medium. The ratio of the speed of light in vacuum, which is denoted by C, to its phase velocity in the polymer, which is denoted by V, is known as the refractive index. Next, we need to know about the Snell's law if we want to understand refractive index. The refraction of light waves for a given pair of medium follows Snell's law. This law states that the ratio of the sines of the angle of incidence θ1 and angle of refraction θ2 is equal to the ratio of phase velocities, which is v1 over v2 in the two medium, or equivalently to the indices of refraction n2 over n1 of the two media. On the right side, there is an schematic diagram of Snell's law, where you can see the incident light is getting on the film sample at an angle θ1, and the refractive index of the incident media is n1, and when light travels through the sample, the light bends in an angle θ2, and the refractive index of the second medium is n2. And if we follow the Snell's formula, we can write n1 multiplied by sin θ1 equal to n2 multiplied by sin θ2. Next, we need to know about the specific refraction and molar refraction. Specific refraction is a characteristic constant for all organic substances, and this was first observed by Gladstone and Dale in 1858, who stated the constant as the ratio n-1 over rho, where rho is the density of the medium. While studying the structural groups in the molecule, they discovered that the molar mass, which is m, and the specific refraction exhibits additive properties, and this equation shows the relationship between the molar mass, specific refraction, and the additive property, where R is referred as the molar refraction. Lawrence and Lawrence in 1880 developed another expression for the molar refraction, which also shows additive properties, and this is the equation for that one. And finally, a simpler expression was suggested by Vogel in the 1950s, which is only valid at constant temperature, and this is the equation for that simpler expression. Since the molar refractions RV, RGD and RLL, which is for Vogel, Gladstone and Dale, and Lawrence contains additive property, they can be computed as a sum of corresponding atom, bond or group contributions. The molar volume can be estimated as a van der Waals volume of the compound divided by the average coefficient of molecular packing. Refractive indices of polymer blends. The application of the Maxwell relations is valid for heterogeneous polymers, and polymer blends with phase dimensions below the wavelength of the incident light and the upper bound of the refractive index of the copolymer can be calculated from the sum of the dielectric constants of the phases. And we know that dielectric constant is equal to the square of the refractive index. And using the additive property, we can explain the refractive index in the following equation, where Ni and V sub I are the refractive indices and volume fractions of the constituent phases respectively. If the refractive indices differ by less than 0.2, the refractive index of the heteropolymer can be calculated by adopting a simple additive approach based on the volume fractions. So this equation is applicable to planes, block or graph copolymers, composites, and finally semi-crystalline polymers. The refractive index of the blend for a semi-crystalline polymer is given by the following equation, where V sub Cr is the volume fraction of the crystalline portion, and this quantity can be calculated from the densities of the amorphous and crystalline phases, which is the following equation, where rho is the measured bulk density, rho C sub Cr and rho sub Am are the crystalline and amorphous densities. Now we are going to talk about the high refractive index polymer. In short, we can say it as HRIP. So what is a high refractive index polymer? It is a polymer which displays refractive index greater than 1.50. The coating materials which have high refractive indices, typically greater than or equal to 1.65, often deliver high optical quality performance characteristics and transparency over the visible spectral range for practical application. When the refractive index of the encapsulant of a light emitting diode is increased from 1.5 to 2.0, the extraction efficiency of the diode almost gets doubled. These are some of the examples of high refractive index polymer. On the left side, you can see an organometallic high refractive index polymer which consists of iron, phosphorus and sulfur. On the right side, you can see an high N polyimide nanocomposite, and in the bottom we can see a sulfur containing polyimide with high refractive index. These are some of the application of high refractive index polymer. Example of CMOS image sensors with optical waveguides is shown on the left side. In the middle we can see a CMOS image sensor, and on the right side we can see LEDs of the 5 mm diffused type. So now comes the questions. A ray of light strikes the surface of a pond at an angle of 30 degrees to the vertical. If it is moving from air to water, what will be the angle of refraction? We know the refractive index of water is 1.33 and the refractive index of air is 1. I hope you can calculate the refractive index and the angle of refraction from our previous discussion. For your convenience, we have shown the explanation here, and you can see the angle of refraction would be 22.1 degree for this problem. Here is another question for your practice. A beam of light hits a crystal at an angle of 31.5 degree to the normal. The light is refracted in the crystal and changes to an angle of 21.2 degree to the normal. What is the index of refraction of the crystal? For your convenience, we have shown the explanation here as well. And finally, you can see by using Snell's law, you will be able to calculate the refractive index for the medium. We hope that after the discussion of all these topics on solubility, degradation and refractive index, you will have a good grasp on the chemical properties of the polymers. Thank you so much for your time and attention.